Okay, today we're going to be start thinking about projectiles. So, up until this point, we've only been considering objects moving in one direction. A projectile is anything that is launched, thrown, or released from in the air. So, projectiles, any object that has been launched, thrown, or released into the air. So we can think of an object here, we can think of throwing up and it coming back down, or like that, or like that. All these are projectiles. Or you can think of, it's meant to be a gun, firing a bullet. Well, this bullet is going to go like that. Or if you think of a tennis racket hitting a ball, the ball is going to go like that until it lands on the ground. We can also think of a table and a ball, and if we roll the ball off the table, it'll go like that. Now, if we look at projectiles more closely, we can think about them as having motion in two directions. So we have this horizontal motion. We give for the bullet coming out, it's been launched in the horizontal direction, and it's got some velocity in that direction, but gravity is also acting on this, so there is also a downward motion because of gravity, and there's also going to be air resistance at play as well. If we think about a ball being thrown in the air, we give it this initial velocity upwards, gravity is coming downwards, but there's also, if it's going straight up in the air, it would just go up and then down. But if you were to throw a ball, for example, it's going up like that, there's also this component of, you always with projectiles have your horizontal component and your vertical component of the motion. And so we need to separate the motion of projectiles into the horizontal and the vertical components. Now, if we were to roll a ball off the table at quite a high speed, and if we were, say, to use at the same time as throwing our ball off the table, we also had one just drop down, straight down at the same time. And if we were to take pictures with a super fast motion camera, what we would see is that we would come up, oh, let's actually get into a fresh page. So if we were to do this, so we have two balls and we release them at the same time, and the motion of the ball that rolls off the table goes like this, and we can, if we were to do it until it falls down there, and the ball that we just release, something really interesting is going to take place. If we were to take pictures of them snapping away, we would find that the time taken for this ball just to drop through the height is the same time that it takes for this ball, regardless of its velocity, it's fired out in the vertical. So it's got this vertical velocity. Sorry, it's not vertical, it's horizontal. This horizontal velocity, regardless of its horizontal velocity, it will take the same time to drop this height as the ball that's just released and just falls straight down. So the conclusion is a ball that rolls off a bench at high velocity will take the same time to hit the ground as one that merely tips off. This also, if you had this was the same principle would be if you hit a tennis ball. Say a tennis ball is a tennis racket. That is a terrible tennis racket. It's tennis balls hit really high velocity. If you just drop the tennis ball at the same point, they would both hit the ground at the same time. Same principle as a bullet fired out of a gun, because the high velocity is its horizontal velocity. If the horizontal, so therefore, the horizontal velocity has no effect on its vertical acceleration. The horizontal velocity will determine the distance it travels. For example, with our ball falling off the table, the horizontal velocity will determine how far the distance is that it goes in the horizontal direction. Obviously, if higher velocity, it would go further in this distance it takes to drop down the vertical. So we treat the horizontal and vertical motions separately. And this is something that you will have to get more really used to, being able to pick which components are for which part of the motion, and it's a really important skill to grow in your physics. So let's look at some examples. So a ball rolls horizontally off a bench with height 1.2 meters. It has initial horizontal velocity of 3.0 meters per second. So here's our table, or bench, whatever you want to call it. So this is our 1.2 meters. How far away from the bench does it land? So that's what we want to find out. So what do we know? Let's consider what we know. We know the horizontal velocity is 3.0 meters per second. Okay, this is what we know in the horizontal. In the vertical, we know that its vertical velocity is 0 meters per second. We know the height is 1.2 meters. We don't know the time. The time is going to be the same for both. So these are else. We don't know the time. We don't know the vertical final velocity, and we don't know the distance that it travels in the horizontal. So what we're going to use is we're going to consider the vertical motion first to give us the time. So we'll use the equation S equals ut plus a half at squared, because the acceleration is going to be 9.8 meters per second squared, because it's the acceleration due to gravity. The initial velocity is 0, and the distance it travels in the vertical is the height, so it's 1.2 is going to be equal to half times 9.8 times t squared, and calculating that out, we're going to find that the time is 0.5 seconds that the ball's going to be in the air for. Now we can just use for the horizontal the simple equation of motion. V is d over t. We know that the horizontal velocity is 3. The distance travelled is what we're looking for, and the time is 0.5. So the distance is going to be 1.5 meters from the bench. So let's look at another example. A stone is thrown horizontally off a cliff. In projectile questions, they like cliffs and things being thrown off cliffs. At a velocity of 5.0 meters per second. It splashes into the water 3.5 seconds later. Firstly, how far from the cliff did the stone into the water? So let's just quickly draw a wee diagram. There's our cliff, here's our man on there throwing the stone. Down there, and the initial velocity is 5 meters per second, and that's in the horizontal. And we know that t is 3.5 seconds. So again, we're just going to use our simple equation of motion. V equals d over t. The velocity is 5. Distance is what we are trying to work out over time, which is 3.5. So our distance is going to be, calculating it out, is 17.5 meters. Next, we want to find out how high above the water was the stone thrown. So we know it took 3.5 seconds to reach to hit the water. So this is we're basically being asked, how high is this cliff? So we can use the equation of motion again. Again, the initial velocity is 0 in the vertical. S is what we want, and A is going to be the acceleration due to gravity is 9.8 and it's 3.5 seconds squared. Calculating that out is 60 metres, the cliff is 60 metres. And finally, what is the velocity of the stone as it enters the water? I'm just going to work this out here. So we've got the vertical velocity, so this is the velocity coming down here, and we'll use v equals u plus at. So remember, we have to calculate the velocity when it hits the water. It's got a vertical velocity and it's got a horizontal velocity, and we need to calculate each component of velocity separately. So in the vertical, its initial velocity is 0 plus 9.8 times t, which we know is 3.5. So the vertical velocity as it hits the water is going to be 34.3 meters per second. Now, the horizontal velocity is 5 meters per second. So we're going to combine done that the wrong side. So this is the vertical velocity. The horizontal velocity is the 34.3. This is the 5. And so we now can use Pythagoras to work out the resultant vector. So we'll call this c, because a squared plus b squared equals c squared. So that's 5 squared plus 34.3 squared is going to give us c squared, which gives us c equal to 34.7 meters per second. It's be a 1, not a 2. And we can calculate the angle of entry is going to be this angle here, theta, which is worked out from the tangent of theta is 5 over 34.7. So theta will give us 8.2 degrees. So we can say that the stone enters at 35 meters per second at an angle of 8 degrees from the vertical, 8.2 degrees. Let's do another one. A ball is struck and leaves the ground as shown. So you can think about this maybe as a golf situation. So as the ball leaves the ground, it's actually been given a vertical and a horizontal component of velocity. So the first part is to calculate the horizontal and vertical components of velocity. So the horizontal, we're just going to use trig for this. It's going to be this part here, so we're going to use the cosine rule. It's going to be 12 times the cosine of 23, and that's going to be 11 meters per second. And the vertical component, again, is going to be this, is going to use sine. 12 times the sine of 23 is going to give us 4.7 meters per second. Next part is calculate the time the ball is in the air until, that's not this unit, not until, its first bounce. So we're going to use the vertical component of velocity. So when the ball returns to the ground, its vertical displacement will be 0. So if you think about the ball, the vertical is going to go up and then down in the vertical motion. So its vertical displacement is 0. So what do we know? We know that its velocity must be negative because it's going to be it's going in opposite direction. Its initial velocity is going to be 4.7 meters per second. So you think about it here, it is given its initial velocity of 4.7, it comes up, velocity here will be 0, comes down, and then it's going to be negative 4.7 because it's in the opposite direction to its as it goes up. The acceleration is going to be minus 9.8 meters per second. The time is what we don't know, and the displacement is 0. So we can use acceleration is v minus u over time. So that's 9.8 equal to minus 4.7 minus 4.7 over time. Calculating that out, we'll get time is 0.96 seconds. And we want to finally calculate the magnitude of horizontal displacement. So this is how far the ball is going in that direction. So the time is going to be the same. So we can use our S equals V over T, where this is going to be our horizontal velocity. So our horizontal velocity was this over 0.96, which is going to be 10.56 meters. So I hope that helps.